Alrighty, everybody. Well, welcome back. And first and foremost, I want to apologize for taking a little bit longer than expected to put out this second video. I can totally see why students ran out of time on the AP exam. Questions 4 through 6 took on average a lot longer than questions 1 through 3. And I think if I had taken the entire 6 questions straight and timed myself, I would have been very pressed on time to finish within the 90 minutes at the level of context and explanation that I like to give with each of my answers. Let's jump right into question 4. So this question was our inference procedure, and my students were very happy to see that this year's inference procedure was a 2-sample t-test for the difference in population means. There was a lot of speculation that because chi-square is going away, College Board was going to make the inference procedure this year one of the chi-square tests. They were just a bit nervous for that, so happy to see that it was a t-test, a 2-sample t-test. The question says, a farmer wants to know whether there's a difference in the mean number of oranges that grow on trees fertilized with the current fertilizer brand C or a new fertilizer brand N. The farmer randomly assigns 58 trees to be treated with each of those two fertilizers, and the number of oranges from each tree is recorded. So this is another experiment. The summary statistics by fertilizer brand are shown in the table below, and again, I would be very happy that they gave you the summary statistics and not the data itself, because number one, you didn't waste time typing those values into your calculator, and number two, you didn't risk making a mistake as you type them. So the question is asking, at the 5% significance level, do the data provide convincing statistical evidence that the average number of oranges on trees fertilized by the current brand is different from the number of oranges on trees fertilized by the new brand for all trees similar to those in the study? My students learned the state plan do conclude method of writing answers to an inference procedure, and so that's exactly the method that I'm going to use to take you through these solutions. All right, so I'm going to start with the state step, but again, if your teacher taught you a different method for answering these questions, that's totally okay. College Board is not grading you based on what information you put in each of these sections, but instead having all of the required information that they look for in an inference procedure. So in our state step, we were taught to label both our null and our alternative hypothesis, in which case I am defining any parameters that I use. I'm saying mu sub n represents the mean number of oranges on trees similar to these fertilized with brand N fertilizer, and mu sub c represents the true mean number of oranges on trees similar to these fertilized with brand C fertilizer. My null hypothesis is going to be that the difference of these two means is 0. The alternative is two-sided. It says that the difference of these two means is not equal to 0. And I mentioned my significance level, 5%. Then we move on to our plan step, where I am naming the inference procedure, again, a 2-sample t-test for the difference of means. And I'm checking my conditions. In this case, there's 2 conditions I have to check because it's an experiment. I need to check that there was random assignment, and there was. 58 trees were randomly assigned to each of the 2 fertilizer types. And I have to check a large sample or a normality condition. In this case, both treatment groups were of 58 trees, which is at least 30, which satisfies the central limit theorem. You did not have to check independence. Again, the 10% condition is only required when you are selecting at random from a population. And in this case, you were doing random assignment, so you did not have to check the 10% condition. The 2 groups are independent. Then we move on to the do step, and this is the most fun step. I showed more work than you had to here, but required as part of the do step, you needed to give the t statistic, the test statistic, the standardized test statistic was 2.202. Degrees of freedom corresponding to that test statistic are 108.174, and a p-value corresponding to that test statistic and degrees of freedom are 0.02977. Please keep in mind, if you went with degrees of freedom of 57, which is the lower of the 2 sample sizes, in our case they were the same, you could have gone with 57 degrees of freedom, would have led to a slightly different p-value, but both would have been acceptable by College Board. And then finally, our conclude step, we're going to compare our p-value to our significance level. I said since our p-value of 0.02977 is less than our significance level of 5%, we reject the null hypothesis. We have convincing statistical evidence of a difference in the mean number of oranges on trees like these that were fertilized with brand C, the current brand, and brand N, the new brand of fertilizer. On to question 5, one of the questions that gave students a little bit of trouble this year. We're looking at an association among professional athletes between their age group and the type of sports that they play, between basketball, football, and baseball. The question gave us a two-way table that summarized that those two variables for all professional athletes in a recent year, both their age group and the sport that they played. And the first question is really, if you think about it, coming from the earliest part of the course, unit 1 or 2, you learn to look at a two-way table and determine a relative frequency. We then, in unit 4, formalize this as a probability. We're being asked to find the probability that a randomly selected professional athlete is a football player. The numerator is 2,461. That is the number of football players. Our denominator is 4,193, the total number of professional athletes among these sports in a recent year. Answer is 0.5869. 58.69% of professional athletes were football players according to this two-way table. The second question is a conditional relative frequency or a conditional probability. We're being asked what is the probability that a randomly selected professional athlete is in the age group between 25 and 30 years, given that they're a football player. So for our numerator, we need to look at how many of our athletes are both football players and in that age range. We got 1,326, and divide that by the total number of football players, 2,461. We get 53.88% for this answer. Next, we are being given a mosaic plot, and what's interesting about a mosaic plot is, number one, it is very useful when we are summarizing the relationship between two categorical variables, and it's sort of the best of both worlds because, like a segmented or a stacked bar graph, you can see the relative differences in frequency, relative frequency, among all the values of the category that's on the x-axis, but additionally you can see the differences in relative size of those categories. So in our case, we can see there were a lot more football players than baseball players or basketball players, and specifically within each sport, we can see the percentage that come from each of the age groups. Part 1 of Part B asked us to look at this formula, x equals b times h. Okay, and it asks us which probability does B correspond to, the probability that we calculated in Part A or the probability that we calculated in Part AII. So in this case, B corresponds to the probability that we calculated in Part A sub I. It is the percentage of all athletes that are football players. Part 2 of this part asks us which probability does x displayed in the mosaic plot represent in context. And I said x represents the joint probability of randomly selecting a professional athlete that is both a football player and in the age group 25 to 30 years of age. On to Part C, we are to see, using the information that we were given, the two-way table and or the mosaic plot, if the two variables, baseball and age group that is 35 plus, are either mutually exclusive, independent, both, or neither. And in Part 1, we're specifically looking at mutual exclusivity between these two variables. I said no. There are 61 professional athletes summarized by the data that are both baseball players and in the age category that represents ages 35 plus. Since both events can happen simultaneously for the same individuals, these events are by definition not mutually exclusive. And then in Part CII, we look at whether the events baseball and 35 plus ages are independent events. In our case, I said to determine if baseball and this event are independent, we should check whether the probability of baseball given age 35 plus is equal to the probability of baseball. Please keep in mind there are many, many, many different ways to prove independence. This is just one of them. No matter what you did, you should have found that the events are not independent. In my case, the probability of baseball given this age category, I got 50.4%, which is different from the probability of randomly selecting a baseball player, which I got 29% for. I concluded that these two events are not independent. And at this point in the question, I can totally sympathize with those of you that were writing this with pen or pencil on paper, because my wrist would be starting to hurt. This question is getting a little bit long. But part D, the final part, says, consider the data of all professional athletes from the two-way table and determine if it's appropriate to carry out a chi-square test for independence to investigate whether there's an association between age group and sport played using this data. And I said, no, it is not appropriate. I saw online there was a big debate about whether this was appropriate or not appropriate. A lot of people thought, yes, it was appropriate because you're looking at a two-way table. You've got one sample with two variables, and that screams chi-square test for independence or association. But the key here is that it was not a random sample. So I wrote, it is not appropriate to carry out a chi-square test for independence because the table includes all 4,193 professional athletes in these sports for that year, not a random sample. Since we already have population data, there is no need to use inference to determine whether an association exists for this population. You have access to the actual data. You can just compute the conditional probabilities and compare them. And finally, we've made it to question 6, the investigative task, a question that a lot of students ran out of time answering. There's a lot of words here. There's a lot of data to look at. It's totally okay if you didn't finish this question. Again, just getting 2 out of the 4 points on the investigative task puts you in a great spot to pass the AP exam. Getting a 3 or 4 on this question puts you in an amazing spot to get a 5 on the exam. I'm going to read you the question, but it says, to win a game, a baseball team needs to score runs. To score runs, players need to get on base, and the primary way players get on base is by hitting the ball. Figure 1 shows the relationship between the number of hits and the number of runs for 30 randomly selected professional baseball teams. Part A, we're being asked to consider a scatter plot of the relationship between the number of hits and the number of runs for these 30 teams. We're asked in part 1 of this part of the question to describe the relationship between the number of hits and the number of runs for these baseball teams in context. My students learned DUFs, and I'm using that acronym and saying there is a moderate, positive, and roughly linear relationship between the number of hits and the number of runs for these baseball teams. There are no major outliers present that I was able to identify from the scatter plot. In general, as the number of hits increases, so too does the number of runs for these baseball teams. In part A, subpart 2, they give us the least squares regression line model for predicting the number of runs based on the number of hits. It is the predicted number of runs equals negative 372.2 plus 0.823 times the number of hits. We're asked to make a prediction using this regression model and a specific goal of 1,250 hits and to show our work. And so I did, and I got 656.55 runs. College Board is now using the scatter plot to overlay a third variable onto this graph. This time it's a categorical variable, whether or not teams are getting a higher total salary or a lower total salary than the median of $160 million. You can see they're representing teams that are having a greater than median total salary with black dots, and teams that are getting less than the median total salary with those white boxes. We're asked to compare the team represented by the point that is circled and labeled with the letter A with the other teams that have the same total salary classification. So I said the team represented by the circled point labeled A is one of the teams that has a total salary that is less than $160 million. Compared to the rest of the teams that share this total salary classification, this team has both the most hits and the most runs. And in part BII, the question gets very interesting because we're being asked to actually look at the relationship, the linear relationship between the number of hits and the number of runs for both sets of teams, the teams making less than the median and the teams making more than the median of $160 million. And we are asked to say whether the relationship is stronger for those teams making more than the median or those teams making less than the median. I said the teams with total salary greater than the median appear to have a stronger linear relationship between hits and runs. The dots are generally more tightly clustered around the positive linear pattern, while the lower salary teams show more vertical scatter in runs for similar number of hits. Now, my students just finished the course with Unit 9, where we learned 2 inference procedures for the slope of a population regression line. Here we're being introduced to 2 other intervals that are possible in the context of this problem. A confidence interval that estimates the mean number of runs for all teams with a specific number of hits, or a prediction interval that predicts the number of runs for a single team with a specific number of hits. We're using the same basic formula that we used in Unit 9, our point estimate plus or minus our critical value t star times the standard error, and just like in Unit 9, we're using n minus 2 degrees of freedom. We are being asked to find the critical value that's going to correspond to a 95% confidence level for both of these intervals, and we're asked to round to 2 decimal places. In my case, I used inverse t. The area was 0.975. That's going to correspond to the 97.5th percentile, which is going to capture between negative t and positive t, the middle 95% of the data. And I got an answer of 2.05 for my critical value for both of these intervals. And in part CII and CIII, we're asked to use this formula to find both of these intervals, starting with the 95% confidence interval for the mean number of runs for all teams with 1,250 hits. My interval goes from 620.74 runs to 692.36 runs. And then again, the same process for the 95% prediction interval for the number of runs for a single team with 1,250 hits. My interval goes from 540.24 runs to 772.86 runs, clearly a wider interval. Part D gets to that point and says, would a distribution of sample means be expected to have more variability or less variability than a distribution of individual observations from the population? And we're being asked to explain. I said the distribution of sample means would be expected to have less variability than the distribution of individual observations, as variability decreases when the sample size increases. From the course, I think you could see on the formula sheet that the standard deviation of x bar, the sample mean, the distribution of sample means, is equal to the standard deviation of the population over the square root of n. You should have made use of that formula in Unit 7, and this question is based on that fact, that as sample size increases, sampling variability of sample means decreases. And so finally, in part DII, which again, a lot of students didn't get to read, we are given 2 standard error formulas, one that corresponds to each of the previously introduced intervals. And we're told that S for both of them is the standard deviation of the residuals, N is the sample size, and X bar is the sample mean number of hits. We want to know, based on the answer from part DI and the standard error formulas for this confidence interval and the prediction interval, why the prediction interval calculated in part CIII is wider than the confidence interval calculated in part CII. And we said the prediction interval is wider because it's predicting the number of runs for one individual team with 1,250 hits, while the confidence interval estimates the mean number of runs for all teams with 1,250 hits. Individual observations are known to vary more than sample means. This is supported by the formulas because the prediction interval standard error includes an additional S squared term, making the standard error larger when S is not equal to 0, as is true in this case, which you can see by the fact that it is not a perfect linear relationship. Since both intervals use the same point estimate and the same critical value, this additional term makes the standard error larger, which automatically makes the prediction interval wider. all in all, I just want to take this opportunity to congratulate you on making it through your AP Statistics course and the AP exam, for making it through these videos and being interested enough to know how you did. This was not an easy exam. Specifically, the time pressure was real, and I know you, as much as your teachers, are looking forward to seeing your score, seeing how amazing you did when the scores come out in July. Enjoy the rest of your week. Enjoy and good luck with any other AP exams that you may have coming up, and have an amazing summer. Thank you for an excellent year.